Okay, let's start the third talk. This is a joint talk about the continuity of entropies. And the speakers are Berta and Bjarne Bergh.
Wonderful. Yeah, very nice. Yeah, so this is a merge talk, and I'm just going to give the first part, and then Bjarne will continue with the second talk. We have very similar results, but we use very different techniques, so we decided to kind of split it that way. Good. So this is joint work with Ludovico and Marco, who are both also at the conference, if you want to talk to them. As I already mentioned, we're interested in continuity of entropy. So first we have to quickly say what is entropy, right? Entropy is a kind of a concept. It's an interdisciplinary concept. It's a measure of uncertainty, and so for this talk, we will mostly just consider the entropy, the Shannon entropy. Yeah? It's defined for probability distributions Px over some alphabet x via this wonderful formula. And then one might be interested in continuity properties of that quantity. I mean, you can see it's important quantity in many areas of research, and hopefully I will convince you also that its continuity property are of some value. Yeah. And of course, you have to say continuous in what kind of distance measure. So for classical probability distributions, a very natural distance measure is the so-called variational distance. It's closely related to how well you can kind of distinguish the two probability distributions. And for this basic setting, we have a tight continuity relation that is shown on the board here. Namely, if the two probability distributions are epsilon close in variational distance, yeah, then the two entropies, or the absolute value of the difference of the two entropies, is at most epsilon times the log of the alphabet size minus 1 plus this kind of binary entropy term apart from each other. Okay, this is a well understood relation. Now, one interesting extension thereof is for the so-called conditional entropy. Yeah, it's just defined as you have like a bipartite distribution. It's just defined as the entropy of the whole system minus the entropy of its parts. So you can think of it as, you know, how much uncertainty you have about x if you are in possession of y. Yeah, and one can extend this notion, and we would not just sequentially use the regular continuity inequality, but one can prove something stronger. Namely, as you can see in this blue equation or inequality here now, the right-hand side, it becomes independent of the alphabet size of y. Yeah? Particularly, it could also be an infinitely large alphabet size. And this is actually quite non-trivial to prove. You have to make use of some involved properties of the conditional entropy. And this was also only shown quite recently. By the way, the references, I have them on the last slide if you're interested. Yeah? And why would we be interested in having something that is independent of y? Like, for example, in cryptography, right? If you have an adversary, you might not know the dimension, or you don't want to make any assumptions about the dimension of that system. So this relation can be quite useful. I will talk very briefly about applications in a minute. But so this is the classical landscape, right? Of course, we're here at the quantum conference. So what we want to do is we want to basically find quantum generalizations of these relations, right? So the quantum generalization of the Shannon entropy is the von Neumann entropy. Yeah, which you can define as this minus trace of rho log rho. And then again, we can ask, okay, how continuous is this? And then the quantum analog of trace distance is variational distance. And then similarly as in the classical case, we basically have the exact same relation. Yeah? And for this case, there's actually a simple proof how you can reduce the quantum case to the classical case. I mean, rho and sigma might have different eigenbases, but you can basically dephase into one eigenbasis and then just use the classical result. Now, where things get interesting is if you want to go to the quantum conditional entropy. Yeah, it's again defined as the entropy of the bipartite quantum states now, minus the entropy of one system. Now, this can become negative, as probably all of you know. Now, in this setting, it becomes more difficult to prove continuity relations. So in particular, in this case, this is from previous work, yeah, in contrast to these relations that we saw before, we don't have tight bounds anymore. So by tight, I mean you know, for every epsilon and in every dimension, you can find states that this inequality becomes an equality. Yeah, so we have this more kind of messy bounds. Good, so this is basically the landscape before we started working on this topic, and in particular, we would kind of like to understand a bit more generically how we can prove continuity bounds, how we can get tight bounds. Now, just very briefly, why would we care? Yeah, so why is that of importance? I mean, in some sense, I just have to convince you, yeah, that entropy appears in many applications of interest. Of course, we can do Shannon theory or quantum Shannon theory. Then channel capacities, they're quantified by mutual information or conditional entropy quantities. Yeah, this is all based on entropy. And then similarly, we can look at entanglement theory. We heard a lot about that already today. Again, entanglement measures are often based on entropic quantities. Even more generally, we can look quantum resource theories. And then if you look at transformation rates, for example, they're usually quantified via entropies. Now, this is just that entropy kind of appears in many theories of interest, but now particularly about the continuity equation, I have here one example. We have many more examples in the paper, but one quantity that is really of interest in quantum Shannon theory is the so-called quantum capacity of noisy quantum channels, and this is often difficult to compute or to find bounds on. And now these continuity relations give you a way of at least finding bounds for channel capacity. So this goes via the so-called epsilon degrading quantum channels. But the point here is just like if you have better continuity relations, you can find better, tighter bounds on the quantum capacity of quantum channels. Good. And then also just a little side note here. Of course, you don't have to only talk about Shannon or von Neumann entropy. You can also talk about more general entropies like Renyi entropies and the like. But this is just very, very briefly why we might care. Good. So now this was kind of the intro. So what is our main result? So one way of stating it in full generalities in terms of this so-called quantum relative entropy that we saw many times today already is kind of a parent quantity which generates all the other entropic quantities that are of interest to us usually. And then the relation we get is slightly simplified. Is not a continuity relation, but a semi-continuity relation, which means that here on the left-hand side, there are no absolute values. Yeah? So what do we get here? Well, so we again start with two states, rho and sigma. They're epsilon apart at most. And then we look at the relative entropy difference relative to some other fixed state, omega. Yeah? And then what we find is an upper bound, which is of similar form as you saw on previous slides. But now within the log is not just the alphabet size, but it's kind of more of maybe an effective dimension, yeah, where you look at this kind of Dmax quantity relative to this state, omega. Good. And now I said this quantum relative entropy is a bit of a parent quantity. So for example, it generates the von Neumann entropy if you just plug in for this omega the identity matrix. Yeah? Or it generates also the conditional entropy if you plug in for the omega this identity tensor the marginal on the B system. Good, so let's see this relation in action. Yeah, so this is the relation from the last slide. Nothing happened yet, but now you can plug in, for example, omega equal to the identity, and then we find this slightly a tighter relation for the von Neumann entropy, where this additional parameter beta shows up. So, for example, if both the states rho and sigma are very mixed, right? And this parameter beta would not be 1, but one could kind of slightly tighten previous relations. And then for the conditional entropy case, so here you see the state omega is the same in both relative entropy terms. So we have to restrict to the case where the marginals of rho AB and sigma AB are actually equal. But then for that case, this is already highly a non-trivial case that people previously thought about, we again get back a tight relation. So again, this means that for every epsilon in every dimension, this inequality now becomes an equality, something that these previous bounds were not able to achieve. Yeah? And you see, compared to the classical case, now in the logarithm, there's not a dimension, the system A, but there's a dimension square. Okay? And this is kind of related to states being entangled or the conditional entropy being negative. Good. It was also conjectured before. Now, how do we prove this? Well, this was also in the title of my half of the talk. Yeah, we do this based on integral representations. In particular, there's this integral representation due to Frankel. And what is really nice about this representation is that it equally holds classically, in the commuting case, and quantumly. Okay, so this was originally came from the classical literature. One can also do it in the quantum case. And the idea here is kind of, you can write the relative entropy as this average over these so-called hockey stick divergences. And here this plus on the right-hand side, it just means that you only look at the positive part. You look at a trace of the positive part of this Hermitian operator. And now you don't have to work again anymore with the quantum relative entropy directly, but you can kind of work with these hockey stick divergences, which have very nice properties. So you can think of it a bit like a trace distance thing. Yeah, you just have this additional parameter gamma, but you have very similar properties as for the trace distance. Good. So proof sketch. Okay, the left-hand side of our inequality, it's now a difference of two relative entropies. So you can reorder the terms now in this integral representation, the ones that depend on 1 over gamma and the other ones that depend over 1 over gamma square. And then kind of the leading intuition for our proof is that at least for the case of conditional entropy, we know that this bound that we showed that was previously conjectured, it has to be exactly tight. So if you choose rho AB to be the maximal entangled state, and then sigma AB to this like slightly noisy maximal entangled state. So everything we do to this expression has to be an equality in this case, yeah? If you plug in these rows and sigmas. Good, then in more detail, so what we actually do is, like for each of these two integrals, we split it up into 3 regions, yeah? And where we like have to, the way we have to choose these intervals now depends on this Dmax quantity. And then on each of these 3 intervals, you bound things cleverly using these mathematical properties of the hockey stick divergences. So I have here one example. So if you look at the left integral on the leftmost interval, then you can use here the triangle inequality for the hockey stick divergences, and then you simplify the expression a lot. But if you're interested in more details about this, please check out our paper. Good. So quick conclusion, because before I hand over to Bjarne. So this is our main result, this semi-continuity relation for the quantum relative entropy relative to this state omega. Most important case that we are now able to treat, which has a lot of applications in quantum information theories, for the conditional entropy. Now, of course, there are many open questions. For example, of course, we would like to have this relation also for rho AB, rho B not equal to sigma B. Or maybe even more generally, we would like to do this for the mutual information and not only for the conditional entropy. Good. But with that, I conclude here. And Bjarne, please.
Thank you very much, Mario. So yes, in the second part of the talk, I would like to show you how you can get this tight continuity bound for conditioned entropy, but not using integral representations, but using a completely different approach that is a new kind of nice and simple entropy inequality. And again, yeah, we get this kind of essentially the same continuity bound if the marginals on the B side, so if you trace out A, are the same. Okay, so what is this nice new entropy inequality? So for this, let's for a second forget about any bipartition and things like this. Let's just say we have 2 density matrices of 1 and 2 on a d-dimensional Hilbert space, such that they're epsilon far apart in trace distance. And then what you want to look at is at this difference between these 2 density matrices, and you can decompose this into a positive and a negative part. And if you do this, then these 2 parts will also be orthogonal. And if you know a bit how this trace distance works, then you know that really the trace distance is nothing else but the trace of either the positive or the negative part, so these will both be equal to epsilon. And what you can do then is you can take these 2 things and you can normalize them, so you can divide them by their trace. And these are things I'm going to call rho plus and rho minus. And then they will satisfy this equation, kind of just from the definition. And turns out this is all that you need to write down a new entropy inequality. So what do we get? We get that the difference in entropies between rho 1 and rho 2 is upper bounded by epsilon, so the trace distance, times the difference in entropies now between these normalized positive and negative parts, plus the binary entropy of epsilon. And you might say, okay, this looks like a nice little inequality, but how useful is this really? Like, what do we ever really know about the entropy of O plus over minus? And turns out, okay, you don't maybe have to know that much. If you just remember this kind of defining property that I had on the previous slide, then you can realize that because Rho plus and Rho minus are orthogonal, and because the trace of 1 minus Rho 2 is 0, these Rho plus and Rho minus cannot be full rank, because then the other one have to be 0, and that cannot happen. And so particular implies that the rank of either of them has to be upper bounded by d minus 1, and so also the entropy has to be upper bounded by the logarithm of d minus 1. And if we just put this into our new entropy inequality, and we say we forget about this minus h over minus term because it's negative, then we get this, and this might already remind you of something. Now, if you look at the right-hand side, you realize if you switch Rho 1 and Rho 2, then this doesn't change. So you can get the same inequality with an absolute value on the left-hand side. And this is exactly this Audenaert fineness inequality, so this tight continuity bound just for the phenomenon entropy, and I would call this a non-trivial result. So it's kind of nice that it follows almost immediately from a new entropy inequality. Before I'm going to show you how we can use a new inequality to prove this conditional entropy inequality, I would like to show you very briefly how we can prove a new inequality, because I think it's very nice and maybe also a bit instructive. What I'm going to use for this are just two fairly basic properties of the entropy. The first one is concavity, or actually a slightly better version of concavity. So what's concavity? Concavity is that if you have a convex combination of density matrices, then the entropy of this convex combination is lower bounded by the convex combination of entropies. And actually, it turns out that this is not quite optimal if Rho and sigma don't share the same support. So kind of as a maximal example, if Rho is orthogonal to sigma, then we actually kind of know exactly how we can write this entropy. We can write it as a convex combination of entropies plus this binary entropy of P. And it turns out we can show that we can kind of find a version of concavity that also includes these cases where Rho and sigma don't share the same support. And this looks like this. So if we define lambda to be the trace of Rho and the support of sigma, then we can prove this inequality, where again on the left-hand side we have the entropy of the convex combination. On the right-hand side we have the convex combination of entropies plus the binary entropy and minus some term, which depends on lambda. And this minus term ends up working out in such a way that, for example, if lambda is 0, so if you back to this case where Rho and sigma are orthogonal, then this term will drop. So you get back kind of this exact decomposition I wrote on the kind of the third bullet point. And conversely, if if lambda happens to be 1, then it turns out that this additional term exactly cancels the H2 of P term. And so you get back normal concavity. And apart from that, the other thing I would like to use is what's known as almost convexity. So entropy is not convex, but it's convex if you add a binary entropy term on the right-hand side. And then this looks like this. OK. And so again, I showed on the top the thing we're trying to prove. And below, I have on the top line this improved concavity, and below the almost convexity. And the only thing I really have to do is I just have to make a smart choice of P, Rho, and Q and sigma. And I would like to pick P and Q like this. This is kind of the only way I can do this, so that P and Q sum to 1, and Q is equal to P epsilon. And OK, then I can replace Q with P epsilon everywhere. And I can divide everything by 1 over P. And now for the first line, I would like to pick Rho as Rho 1 and sigma as Rho minus. OK, I can do that. And for the second line, I would like to pick Rho as Rho 2 and sigma as Rho plus. And you might ask, OK, why are you doing this? Well, so the point is that the left-hand side here is still equal. This really just follows from this equation I've already shown a bunch of times, kind of the defining thing of Rho plus and Rho minus. And with these, I can now merge these two equations. And you will see, OK, we have a binary entropy term on both sides, which you can cancel. And you can shuffle some terms around. And this already looks pretty close to what we're trying to get. So we're almost there, but we still have not quite the binary entropy of epsilon on the right-hand side. And to show how we get to the goal, we really have to use the definition of lambda, which with these choices of Rho and sigma that I made, just ends up being this. So the trace of Rho 1 on the support of Rho minus. And if you kind of go back to the defining equations, it's not so hard to figure out, I unfortunately don't quite have time to show this, that lambda plus epsilon ends up being upper bounded by 1. And that's kind of important and nice, because it then allows us to use concavity of the binary entropy to show that this kind of complicated looking term on the right-hand side, this lambda plus epsilon, binary entropy of epsilon over lambda plus epsilon, is actually upper bounded by the thing we're trying to get, the binary entropy of epsilon. And that's it. It's kind of a very, very simple proof if you have this improved version of concavity, which I think we're the first ones to really kind of realize that this holds. With this, then I can use this to prove our actual kind of maybe goal, this continuity bound for conditional entropy. And similar to what Mario was just telling you, we actually get a kind of slightly stronger version in terms of a relative entropy semi-continuity bound, where the second argument is the same. And the slight difference being compared to what Mario just presented you, that in this kind of epsilon log of e to the d max, we get a rho plus instead of a rho 1. Otherwise, then the conditional entropy bound we conclude from this ends up being the same. How does this follow from our new inequality? Well, actually, it's quite simple. If you remember, just at the beginning, I told you how we can get this continuity inequality for the phenomenon entropy just from our new bound. And for this, we kind of use that if rho plus is orthogonal to rho minus, then we can bound this difference in entropies like this. And turns out you can do a very similar thing for relative entropy. So if rho plus is orthogonal to rho minus, then this difference in relative entropies is upper bounded by now a term involving this logarithm of e to the d max, so kind of like an analog of the dimension. And using this, what we have to do basically is just use the definition of the relative entropy. So relative entropy you can write as a minus of an entropy term. So kind of, let's see if I can get a mouse here. So kind of minus of an entropy term, and then minus a trace rho log sigma term. And so the difference between these two relative entropies looks like this. And for the second part at the end, I can use this blue equation again that I've used many times. And for the first two entropy terms, I can use a new inequality. There's now kind of a 1 over 2 exchange, but that doesn't really change anything. And now if you look at the third line, you realize, okay, this is really nothing else but epsilon times the difference in relative entropies, but now with rho plus and rho minus. And to this, I can apply our new lemma that I have on the top of the slides to conclude this bound, and then you can get the conditional entropy bound in a very, very similar manner. So to wrap up, maybe kind of one final remark before I come to questions. This new inequality actually also works in infinite dimensions, which is very nice. And yeah, Mario basically already mentioned the big open question. So we'd like to get these continuity bounds also for rho 1 and rho 2 with different B marginals. We don't know how to do it, but we think it'd be very nice and kind of conceptually very similar, but maybe slightly more general, how we would like to have good upper bounds on differences of relative entropies, also if the second argument changes. With that, I conclude, and I'm looking forward to questions. Thank you.
Thank you very much for a nice joint talk. We can take several questions.
Thank you for the nice talk. I just wonder if your arguments won't work in infinite dimensional setting for example, continuous variable quantum systems, or do you have any continuity bounds in those systems too?
So I didn't quite understand the last part of the question, but I guess kind of if you're looking at these bounds, there always is some dimension in the right-hand side, right? So there's no obvious way to phrase this in infinite dimensions. I guess you could do some energy constraint things, and people have done this, but okay, it's not really what we're focusing on here. I'm not sure if that answers the question.
Yeah, thank you. So.
Yes, I mean, so the B system can be infinite dimensional. That still holds then, these bounds. But if the A system is infinite dimensional, yeah, then you don't have continuity in general, right? So yeah, you could do energy constraint things, but we tried a bit, so it's not necessarily clear how our proof techniques would cover that, but that's another interesting open question, yes.
Thanks for the talk. I'm wondering whether this would generalize to giving a bound on conditional minimum entropy or maximum entropy.
It might. I mean, you can look at continuity property of Renyi entropies in general. Previous techniques did generalize to that setting, and they have also been researched in detail. So here things might also work. The problem is with these integral representations that we use, they give a different family for Renyi divergences. But for the min-max end, maybe you could do something. I will also say that they're much less continuous, right? Here you have a log of the dimension, basically. So once you go to these other measures, you basically go to a dimension term there. But might still be useful. Sorry.
Yeah, no, I guess similar things. So kind of this entropy inequality that we use is really kind of tailored for proving these bounds just for entropy and not for any entropies. I suppose you can kind of think of them in a certain way that we're using like this almost convexity and concavity. And these are kind of similar to techniques people have also used for Renyi's, but it's also not obvious kind of how we generalize our techniques here.
Thanks.
Any question? We have one more question. Time for one more question.
Thanks for the talk. Actually, I have two questions because you have two. The first question is that when I use the entropy continuity property, I usually find that the dominant term is like the binary entropy term. So the other term is linear in epsilon and with a dimension factor. That part usually doesn't, it's not the dominant part. So is there a way, I mean, in your proof, is there a way to find that, is there a sufficient condition for the states so that we have this binary entropy part? Sometimes it disappears, and sometimes it is there. Okay, this is the first question. The second question is, you said that it is true in infinite dimensional setting, and what is the dimension factor in the infinite dimensional setting case? Yeah, that's my questions. Thanks.
Okay, maybe I can answer the second question first. So what I was referring to there really was this inequality involving the Rho plus and Rho minus. So in that case, you don't have any dimension factors appearing. So that's why this works still in infinite dimensions. Maybe you want to answer the second question.
Well, yeah, for the conditional entropy, just the B system in our case can be infinite dimensional, so it's not in the bound, right? So then it's fine in that sense. For the first question, I don't know. But indeed, yeah, right, if you're not only interested in the trace distance, right, between rho and sigma, but in other kind of properties of the states that give better continuity relations, one could explore this, but I don't have a smart answer.
Yeah, let's thank the speakers again. And we'll have a 30 minutes break.